Okay, today's study tip says if the exam is at 12 o'clock, stop studying at 10 o'clock. Rest your brain, feed your brain with healthy food, then breathe deep breaths. Every exam is stressful, I get it, but a lot of you are cramming the last half an hour right before. As I'm passing out the test, you're trying to shove in as much stuff as possible. Please think about using this tip because just taking a half an hour before to calm yourself will lower your heart rate, right? Lower your blood pressure, will make you less anxious, and having that high blood pressure, that anxiety, of course, makes mistakes on the exam. So one of the problems is you've got to finish your studying. You've got to be done at 10 o'clock or whatever time you pick. You can't say, oh, I'll review that and do it one more time right before. You have to set your time. Pretend the test is an hour earlier. So instead of, being our normal start time, pretend it's an hour earlier, and then you'll, eat breakfast or lunch or whatever it is. Calm down, play a game, call a friend. Just relax for a little bit, okay? You'll feel much more confident on the test if you can control that blood pressure and heart rate. Chapter 14, Part 1 today, cardiac output, blood flow, and blood pressure. So we have 2 lectures on this topic. This is some good physiology today. Okay, so as you know, we're getting into this pretty deep now. This is one of the tougher topics, I would say. Okay, so here's the equation that I taught you on the first day in lab. It says cardiac output equals heart rate times stroke volume. So the cardiac output, remember, is in the units of liters per minute, or you can do milliliters. In this case, it's 5 to 6 liters per minute. So if you got the 2-liter soda bottle, which you will not get because you're not going to drink soda because that is junk food and it's nothing good in soda, nothing. So pretend you have 3 of those 2-liter bottles. That's how much blood you have in your body, and that's how much goes around each minute. So if you follow 1 drop of blood, little drop would take 1 minute to go from your heart all the way out and back in again. The heart rate, as you know, is beats per minute. So you did this several times, of course, and especially on the first lab, right? The stroke volume is the amount pumped out in each beat. And here we have, because it's a small amount, we have it in milliliters instead of liters. So the stroke volume is the milliliters per beat. You can calculate this if you take the end diastolic volume. So diastole, remember, is when the heart is relaxing and it's full. So at the end diastolic volume is about 135 milliliters. So if you get your water bottle, it's one of the things I always use as an example, of course. It's your 500 milliliter water, the little one, and just take, a third of it. That's about how much you have. This is usually, of course, going to be in the left side, so we're going to talk about the left side. The volume minus the end diastolic volume minus systolic volume. So when the heart squeezes or contracts, there's still 65 milliliters left inside the ventricle. So you subtract the 2 and you get 70. This is the amount of blood pumped with each heartbeat. So we squeeze, and not all of it comes out. It's not completely empty. Now what we're going to do with this is we're going to change all these numbers to increase or decrease our needs based on exercise or sympathetic, parasympathetic. So we're going to learn about how to regulate cardiac output. Okay, so here it is. Same equation, cardiac output equals, they write cardiac rate, I say heart rate, times the stroke volume. So first we're going to look at how we can change the cardiac rate. So we can change it with the parasympathetic nerves or the sympathetic nerves. What I want you to see in this picture is every time there is a solid line on an arrow, that means it has a positive interaction or a positive influence on that heart rate or stroke volume. Okay, if it has a dotted line, this means it's negative. Okay, so let's look at how parasympathetic and sympathetic change the heart rate. So there, as you know, is the pacemaker, the SA node, and it has its pace, and that's how fast the heart goes, right? There are, in this picture, a reminder first that this is the pacemaker potential. So remember, the autorhythmic cells have their own pace. They slowly reach threshold, and then you get the action potential. Then they slowly reach threshold, and then you get the action potential. We talked about how this happens over and over and over again since you were a little embryo. When the SA node is innervated by the sympathetic nervous system, what happens is the time to reach threshold is much faster. So compare this red line here at the top. It's kind of long, drawn out. This one's super short. But the action potential, the yellow line, is exactly the same. Do you see that? So the action potential is the same, just the rate at which we reach threshold is much faster. So here, boom, boom, boom. So in this time where we have at the top, the control has 2 action potentials, we have then 3. So it's faster with the sympathetic nerve. The parasympathetic, as you know, slows down the heart, and it also innervates the SA node. If you go down here and look, the red line is just showing how long it's taking to reach the threshold, but still the same action potential. But then we wait, and then we get another one. So we got 1 action potential instead of 2, and here with the sympathetic we got 3. So the way that the sympathetic and parasympathetic nerves change the pace is by changing the rate at which we reach threshold. Notice that the action potentials are the same height, right? The action potentials don't change height. But this will then make the heart rate go faster or slower, right? So with sympathetic, makes it go faster, parasympathetic, slower. You already know this. So altering cardiac output by changing heart rate. So now we write it down. We increase heart rate with the sympathetic nervous system, and its neurotransmitter is called norepinephrine. And we increase the pacemaker action potentials. We decrease heart rate with the parasympathetic nervous system and acetylcholine, and we do that by decreasing the pacemaker action potentials. So I need you to learn the names of those neurotransmitters, norepinephrine and acetylcholine. Okay, back to the picture. We got the first part. So now we look at stroke volume. We're going to look at the sympathetic nerves coming over. In the picture, they draw like a double arrow here, right? So the sympathetic nerves can change the strength of contraction, and of course, if the contraction is harder, stronger, then you're going to get more volume being pushed out, right? The other thing is changing the end diastolic volume, so I'll explain that to you. And the third thing, which has a negative effect, is the total peripheral resistance and the mean arterial pressure. So let's go through each of those. We can alter the cardiac output by changing stroke volume. So we increase stroke volume. So what was that number before? Where's my notes? 135, right, was the end diastolic volume. And we subtracted the end systolic volume of 65, and we got 70. Okay, so what if we make the 135 155? What would happen to the stroke volume? What would it be? If we made the 135 to 155, and we subtract 65, we would get 90. We add 20 more. This is called the Frank-Starling heart of the law. When the end diastolic volume increases, there's like when you put more fluid into the ventricle, there is almost like a rubber band kind of effect. If you stretch it more, you stretch a rubber band, you want to shoot a rubber band at a friend, you stretch it a little bit at your friend, and you let go, the rubber band doesn't go very far, right? But if you stretch the rubber band even farther, you let go, of course it goes shooting across. So the Frank-Starling heart law of the heart is named after these dead guys, Mr. Frank, Dr. Frank probably, and Dr. Starling. And they discovered that as you increase the volume, that increases the strength of contraction of the heart. It's probably due to the more of the elasticity of the heart. And your lungs kind of do something similar, right? If you stretch them, they exhale more. So if you stretch the ventricle muscle, it will respond with more force to push out blood. So what will cardiac output do? What do I want to write here? Decrease or increase? Increase, right. Next is the total peripheral resistance. Another way to change stroke volume. Total meaning everything. Peripheral means your arms and legs. Resistance means to stop. Okay, so stopping from all of your arms and legs and your body. That's due to, well, it's due to a couple things. Let's see what's on the list here. It says, with resistance in arteries, it's difficult to pump the blood. So if you have a plugged artery, you're going to have, let me ask you this. If you have a plugged artery and you're trying to push fluid out of your heart through a plugged artery, what's happening to resistance? Is there more or less resistance with a plugged artery? More resistance, right? So then it's harder, of course, with more resistance to pump the blood. And if you have more resistance, what happens to cardiac output? It will, like, you can't get it out, right? So the cardiac output will decrease. So the more resistance you have, the harder it is to pump, and so the cardiac output will decrease. Another example of total peripheral resistance is body weight. So if I gain 100 pounds, my capillaries and arteries and venules, they grow to feed the extra 100 pounds. So the distance then that my body has to send blood is now a lot further, right? So from my heart, if I send blood out to my feet and back now, and then if I gain 100 pounds and I send it out to my feet and back, I'm going to have a lot further distance, right? I have a lot more blood vessels to travel through since I gained 100 pounds. So the resistance goes up, and therefore it works my heart a lot harder. My heart has to push a lot more in order to get the blood down to my feet and back if I gain the 100 pounds. And of course with that comes blood pressure, right? And problems with stroke and all that stuff. So we'll talk about that more probably in the next lecture with flow, okay? Cardiac output and flow. Sympathetic nervous system also increases the strength of ventricular contraction. It increases the stroke volume. The nerves release more calcium. Of course, with more calcium, you get more strength of contraction, right? So what will happen to cardiac output if you turn on the sympathetic nervous system? It will, what do I write here? Decrease or increase? Increase, right. Okay, so those are the big things. Cardiac output equals stroke volume times heart rate, and you need to be able to tell me how we can adjust and change all of those things. Any questions? Next topic is about fluid. So in relationship to cardiac output, of course, the more fluid you have to move, right, you have to have a bigger cardiac output. So if you have a look at where is all the fluid in the body, and just think about it. Where do you think of fluid in the body? So you know you have cerebral spinal fluid, right? Amniotic fluid. You know, you think maybe bladder has fluid. Well, it turns out that's not really where most of the fluid is. Turns out a lot of the fluid is inside each little teeny cell. So you never really think of that. But inside is the cytoplasm. That is where we carry most of our fluid. And then anything outside, I'm looking at the top of the picture here, it says intracellular and then intracellular and extracellular fluid. The extracellular is actually divided into two subcategories. The blood plasma, remember, is the water part, right? So not all the blood, just the plasma is, of course, a big part. But even bigger is the space between the blood and the cells. So that's called the interstitial fluid, right? So that's our main water compartments, or main fluid compartments. First is the intracellular fluid. Intra means inside, right? Inter, what does inter mean? It means between, right? Inter means between, so this is intracellular, inside, which means the cytoplasm. Second, the extracellular fluid means anything outside of the cell, which includes the interstitial fluid between the cells and the plasma of the blood. I want you really in this picture to see that these arrows are going back and forth and back and forth, and the fluid can move, and we're going to talk about which way the fluid moves, but I want you to know that blood is the king. Okay, so when we look at which way does the fluid go, the person or the spot that always bosses everybody around and says where and what goes where is the blood. So the blood has got to keep happy. The blood is the king. Okay, so you need to remember that when we're talking about which way these fluids go. We've got to keep the blood happy, because if blood pressure falls or blood pressure gets too high, we die. Okay, so we got to keep that blood pressure. What's the next page? Oh, two pressures to know. Okay, so fluid, of course, has pressure, right? The more fluid you have, the more pressure you have. If you have a pool full of water, you have a lot of fluid, and of course it's very heavy. If you just have a cup of water, it's not very much pressure. So there are pressures that tell us which way things move. These pressures are used to determine fluid volumes and the movement of water in and out of blood vessels. So first one, called hydrostatic. What's hydro mean? Water, right? Static, again, like stasis, stable, keeping the water pressure level. Okay, so it's the force of a fluid on the surrounding wall. It's called the hydrostatic pressure. So it's the force of the water pushing. Second is called the colloid osmotic pressure. This is the force due to a protein's attraction of water. So remember your friend from Physio X1? Albumin, the giant 66,000 molecular weight protein. You have a lot of it. Albumin is in your body. The one I have researched before was egg albumin. I used to work on proteins in graduate school. That one you just get from chicken eggs. So this albumin is everywhere, and it attracts water and it holds water. Because of the attraction, it actually says, we say it has a force. So we call it the colloid osmotic pressure. Okay, so what I want to do is show you where these pressures are. I want to show you a blood vessel, where the pressures are, and I want to actually do some calculations in math, some good physiology. And this is physics, right? Physiology has the word physics in it too. This is how your book explains which way the fluids go, and why they go. Remember, why would it come to the blood? Because the blood is king, right? And this is a little scary, so I've kind of dissected it, this same picture, into my own picture. Okay, so we're going to draw this picture of a capillary. The left side is going to be oxygenated. The right side is going towards the veins. Okay, so the left side arterioles. We'll assume systemic circulation. When I write the capital letter P, if you look at the little of the bottom box here, it says P is hydrostatic pressure. What's this letter here? This is pi, right? Which is a type of P, which still means pressure. If you see pi, you're going to say osmotic pressure. So there's a little key here. If you see C, that means capillary. P, it means plasma, and I means interstitial fluid. Okay? So what I want you to do is just listen to me. Don't write this down. Okay, you can stop, you can pause it in a minute and write it down. I just want you to listen to me while I explain this, okay? So the first thing is that in the capillary, we're going to look at the two pressures that we have, the hydrostatic and the osmotic, and I'm going to give you the actual numbers, okay? So don't write this down, just listen, okay? The hydrostatic pressure at this end of the capillary is 37 millimeters of mercury. mmHg is millimeters of mercury. And you know your blood pressure, when you say what's your blood pressure, the numbers are like 120 over 80, right? So you can see this is kind of getting pretty low now. 120 over 80 is on your arm, right? You measure blood pressure on your arm. This is getting way out past your arm into a little capillary, and so of course the pressure falls as you go farther away from the heart. This pressure is water, of the water inside, the 37, right? Water inside, and this pressure makes the water want to go out. So you won't see this in the book, this out thing. This is my way of trying to translate this difficult topic. Okay, so this 37 is the water inside the capillary trying to get out. We also have the, how do you say this? If you see pi, you say osmotic pressure, and P, you say plasma. So this is the osmotic pressure of the plasma. This is the force member of the albumin. It's 25 millimeters of mercury, and it wants to keep fluids in. So I'm going to write the in here. Okay, so we have one pressure trying to push things out, another trying to keep fluids in. On the interstitial fluid right outside, we have a, how do we say this one? Hydrostatic pressure of the interstitial fluid. Its number is 1. And it wants to, this pressure here of the interstitial fluid, the hydrostatic, is trying to push things into the capillary. Okay? Just like this one was trying to push stuff out of the capillary, this one's trying to push it in. And if you look at the last one, which is the osmotic pressure of the interstitial fluid, it's actually 0. So this, remember, is due to the albumin. There should not be any proteins out here causing that to happen. So the number is 0. So if we add these up, 37 out, 25 in, 1 in, what's the net filtration pressure at the bottom here? Okay, so see if you can do this. Pretend like it's a negative and a positive, or positive, negative, negative. Pretend like you're adding positive and negative numbers. Okay, and then write down on the bottom what the net filtration pressure is. Okay, 37 out, 25 in, 1 in. Your grand total is the net pressure equals 11 millimeters of mercury pushing out. And there's a name for this. To get the fluid out through the little teeny capillary bed here, through the fenestrations, remember all those words, in the basement membrane, that's called ultrafiltration. So filtration happens in your kidneys. Ultrafiltration is what we call this. Okay? Write this down. Take a minute, pause the show, and write these on your figure so that you have them. All right, next, on the right side. So what do you think happens to blood pressure as we go way down to the other end of the capillary? Do you think you increase pressure as you go farther away from the heart, or do you decrease pressure as you go farther away from the heart? And you can think, the vena cava, right? Which is at the very end, after you've pushed out of the aorta, right? Which one has the lowest pressure? The arterial side or the venous side? In this case, we're going to drop down actually to 17. So the pressure went from 37 to 17 simply because it got slowed down as it goes through the capillary. And now we're at 17 millimeters of mercury pushing out when we get to the venous end. Notice the proteins don't change. So the osmotic pressure is the same at 25. Remember, that's trying to keep fluid in. The outside also does not change. So this is still 1 millimeter of mercury pushing in. And the proteins do not change. So that's 0. So what's your total now? Do the math on this. If you have 17 out, 25 in, 1 in, what do you get? You get net filtration pressure of 9 millimeters of mercury trying to push stuff in, right? Coming back into the capillary. This is called reabsorption. Okay, so absorption is when we bring nutrients into our body in the digestive system. So this is reabsorption, meaning repeat, right? To do it again. Okay, so that means this capillary has fluids getting pushed out and fluids getting pushed in. But notice, are the numbers equal? So we have 11 and we have 9. So what ends up being a problem? If it's not equal, then that means that the fluid that's coming in coming out is not also going back in. So where's the leftover? Inside the capillary or in the interstitial fluid? The leftover is sitting in the interstitial fluid. Who picks up the leftover? If you have some extra fluid in your interstitial fluid, what part of your body picks that up? Any extra? That would be the lymphatic system that picks it up. So we have lymphatic venules, right? We don't have lymphatic arteries, right? Just venules and veins, and then dumps back into the heart, into the capillary, or the large vessels near the heart, right? So all of this, by the way, is to not only keep the blood happy, but to deliver nutrients. We have to, when you're in the capillary, the whole point is to give nutrients, right, to the surrounding tissues, and then to pick up any waste. So we have to have this ultrafiltration and reabsorption. I don't really know why it's not equal, but if you want your lymphatic system to clean things, it's important to not have it be equal, right? Lymphatic system has a job of taking things through the lymph nodes where they get cleaned and they meet white blood cells and all that good stuff. Okay? So did you write this down on the right side? This is a tough topic. You might have to listen to it again. Okay? The purpose of this is fluid exchange, is to feed the tissues. Okay? To feed the tissues. And this is just explaining all these numbers, how and why fluids move. Okay? Here's a question. It says, Marion has been diagnosed with breast cancer and is about to receive surgical treatment. The doctor tells Marion that there will be removal of her right breast and right axillary lymph nodes. The doctor then warns Marion that a side effect of this surgery may be a swollen right arm. Why would it be swollen? Asked Marion. Tell Marion why her arm may be swollen. Okay, so pause the show, make some notes, and think about this in relationship to what we just talked about. Okay. Where's your axillary region? Point to your axillary region. Good. If those lymph nodes are not there, what happens to the fluid in the right arm? So the extra fluid in the right arm is picked up. What are the lymph nodes that pick up the right arm fluid? Do you know? Do you know your anatomy from this? Yes, they're in the axillary lymph nodes, right? That picks up the extra fluids. So when you get a cold, right? You get swollen lymph nodes in your neck. So we have areas, of course, that have all the lymph nodes for draining. Okay, so if they remove the axillary lymph nodes, and by the way, why would they remove the axillary lymph nodes? If the cancer is in her breast, where does the breast tissue drain? Into the axillary lymph nodes. Yeah, so the breast tissue drains into the lymph nodes. So they must have found some cancerous cells in her lymph nodes. So they're going to remove those two, remove the right breast. What's that called when you remove an entire breast? Called mastectomy. And then her right arm now is going to have the side effect of not being able to drain. So what does she do for her arm? She had the surgery. Let's say she had the surgery. She's feeling good. She got the cancer removed. She's recovering. Her arm is swollen though. So she can wear a brace. There's different kinds of braces that people wear. She can, which would be like real tight, right? So that the fluid doesn't go down into her arm. She probably walks around not with her arm hanging down, maybe casually kind of, is always touching her shoulder or maybe her neck. Maybe she's always rubbing her neck and it looks like her neck hurts, but really she just wants to keep her arm up, right? And of course it would come down faster, the fluid, if she put her arm up in the air, right? But that's a little awkward. So where will the fluid go? Well, there are, of course, other lymph nodes, right, in her chest, in her neck, and other places. And so that will take the fluid, but it's going to take a lot longer to get rid of it. Pretty much cut off, the lymph nodes, which means the access then is gone. Today, this surgery is done much better. This is a story probably from the 80s. This is how they used to do it. Now they're much better at detecting. I mean, there are probably more than a dozen axillary lymph nodes, and they just used to remove all of them. And now they can actually go find which one. They label the cancer cells and then find each lymph node. I think it's done with radioactivity. They find the exact axillary lymph nodes that have the cancer cells and just remove those 5 or 6, because it was a problem to live with a swollen right arm, right? So I've heard that it's much better now today, so that's good. Okay, did we get everything? Swollen? Yes, done. The regulation of blood volume. The kidneys are the organs that regulate, because urine and blood, they're opposite of each other, right? If you need more blood, you need less urine. If you need less urine, you need more blood. So kidneys are the organs that regulate the hormones and have the hormones. Kidneys are the organs that regulate, and we have hormones that command the kidneys. So some of these hormones, they are your friends. This one, antidiuretic hormone, increases water reabsorption in the kidneys, And if you save water, what will happen to blood volume? It will go up. Right. Second one, aldosterone, also your friend, increases the salt reabsorption in the kidneys. The water follows the salt, so blood volume will increase, right? Next one is called renin-angiotensin system. Some people call it renin. I like renin. Renin signals the production of angiotensin 2. Now when we get to the kidneys, we will go through all the steps of how you get from renin to angiotensin 2. For now, I just need you to know that renin from the kidneys, obviously, right, eventually signals the production of angiotensin 2, which then releases the aldosterone, and you already know this, then blood volume will increase, right? And the last one is atrial natriuretic factor. Atrial means what? From the atria, from the heart. Natriuretic, what's a retic do? What's a diuretic do? Makes you lose water, right? And natriuretic makes you lose natrium. What's natrium? Chemistry. Na. What's Na? Sodium. Right, so atrial natriuretic factor is a hormone from your heart that tells your body to lose salt. So it's produced by the atria of the heart, increases the excretion of salt into the urine, and blood volume will, let's see, if there's salt in the urine, water follows the salt, then the water is going into the urine, leaving the blood, so the blood volume will decrease. Right, did you get that? So notice that they're of all four of them, this is the only one that is a decrease thing. Okay, any questions? Last topic for today is blood flow. Now, blood flow and pressure, this is looking at your heart. Squeeze, squeeze, squeeze. Remember I said 120/80? So if you go to your arm, you measure 120/80. So this is looking at blood pressure on the left, 0, 20, 40, 60, 80, 100, 120. This is looking at distance from the heart, arteries, arterioles, capillaries, venules, veins. So we go 120, 80, 120, 180, and then as you get further away, what happens to resistance? Does it increase or decrease? As you get further from the heart, the resistance increases because these arterioles are getting smaller, right? Smaller, smaller. So the example I usually give is, you know, what happens to resistance when you get in a small tube. Like if you're going to drink soda out of the big straws, right? The giant straws, it's real easy. But if you want to drink soda out of a little teeny coffee stir, you know, the little plastic ones, you can't get much flow because there's so much resistance. So as we go from the small arteries and to the arterioles, we drop, 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 drop. Then we get to the capillaries, and you actually know this number. So remember that picture we just spent so much time on? The hydrostatic pressure is 37. So if you go over here, this is about right, 37, about right here. And then on the other side, on the venule side of the capillary, what was the number? Do you remember? It was like 17. So right there. So we slow down, we have less pressure, and then of course the very end, the venules, and then the vena cava has the lowest. And you get back to the heart and it's 0. Okay, so as we go further from the heart, pressure drops, and we'll talk about how that's important for flow. Okay, so, oops, wrong way, sorry. So blood flow, blood moves from an area of high pressure to low pressure. Does that make sense? If I go to the backyard and I want to turn on the hose, I crank the spigot and the water flows from high pressure right there at the house to low pressure at the end of the hose, right? High to low pressure. Pressure changes as you move through the circulatory system. Flow equals a pressure gradient divided by resistance. So flow equals P divided by R. Pressure divided by resistance. So let's think about that. The units are volume of blood per time. So you already know this. Cardiac output is a flow, right? It was liters per minute, right? So it's a volume per time, liters per minute. The pressure is the force of a fluid on the vessel wall. You know that. And the resistance is anything that opposes the flow. Okay, so resistance tries to stop it, right? So let's try this. If pressure increases, just using the equation, flow equals P divided by R. If pressure increases, the flow will increase. And that makes sense, right? If I go to the backyard to turn on the hose, if I pump it up really high and increase the pressure, tons of water is going to come flowing out of my hose, right? So if I increase the pressure, the flow will increase. And if the resistance increases, so let's say I have that coffee stir, okay? So I have a lot of resistance in that little teeny coffee stir. I'm trying to drink my coffee with it, which is ridiculous. I should just go get the big straw from Lee Sandwiches, right? That's the best giant straw. So if the resistance increases through my little coffee stir, what will happen to the flow? It will decrease, right? Okay, so this is introduction to the blood flow part. We're going to do a lot more of this. We're going to do a whole lab on it, and we're going to talk about it next time. All right, let me know if you have any questions. We are done.